Hello students, today we'll see the electromechanical system with a magnetic field as well as with an electric field. We'll see the terminologies used in these particular systems, and finally we'll arrive at the energy balance equation used to solve these systems. So as you can see in the figure, we have a voltage source V, we have an inductor L, the resistance R, the current flowing through the winding is I, the flux phi which is being produced because of the current I flowing through it, M is the mass of this particular object, my K is nothing but the spring constant, my D is nothing but the damping constant, my x0 denotes the equilibrium position. That means when there is no force acting on the mass m, at that point in time what would be the position in which my block m is kept. So moving ahead to the system. Now this was the electromechanical system with a magnetic field. As you can see, it is labeled. Now we'll move ahead to the next. We'll move to the electromechanical system with an electric field. So in the previous case, you saw there is no connection between M and this particular core section. Next, we'll see is here you can see that since this is a electromechanical system with an electric field, so you can see a physical connection here. So the rest of the terms are same. So here let us move ahead and let's see. Okay, we did not discuss two terms, that is F and Fe. So F is nothing but the external mechanical force which is applied, whereas F is uh, the external mechanical force, whereas Fe is the electromagnetic, or it can be electrostatic force as well. Okay, so now let us have a look at certain equations. Now since we have already seen the figure, let us try to form this figure in terms of equation. So as we had seen that we already have a voltage source, so the voltage equation could be written as IR plus L into di by dt plus EF. Now EF is nothing but the voltage drop which happens across the field winding. So EF is the term which you can see in the second figure, that is here. Okay, so moving ahead, the dynamic behavior of the translational mechanical system given by Newton's law of motion, which is F is equal to m into d square x by dt square plus d into dx by dt plus k into x minus x0 minus Fe. So now the total energy supplied by the electric source, that is W capital E, which is equal to integration of V into I dt. Now here we know what is V. We have already seen here in the first equation. Similarly, we have the total energy supplied by the mechanical source is W of capital M, which is equal to integration of F into dx, And similarly, here in the equation 4, we know the value of F, which we have seen in the equation 2. So let us first substitute the value of V from equation 1 in the equation 3. So if we substitute that value, we can write WE, which is, instead of V, my first term is IR, okay, and this is VI. So R is a constant, so it comes out of the integration. So we have integration of I square into dt plus my second term is L into di by dt. Now this would be multiplied with I, okay. So L into integration of I into di is what I'm left with. The last term is EF. So integration of EF into I is into multiplication. So EF into I into dt. Now if you look here, the first term is nothing but the energy loss due to the resistance. I square R, as we say, which is WEL. If you look at the second term, it is nothing but the energy stored in the electromagnetic system. So this is nothing but my WES, and the final term is my WE. If you can recollect what is my W of small e, it is the energy transferred to the coupling field by the electrical systems. So I can write my WE, which is equal to integration of WEF into I dt, where WE is the energy transferred, so we are only concerned with the last term. Now similarly, we'll do the same thing for the mechanical system also. So we know that Wm is equal to integration of F into dx, and what is F, that we have seen in the second equation. So we'll again substitute that. So what we get is W of capital M is equal to M. Now mass is would be a constant number, so we'll bring it out of the integration. So capital M into integration of d square x by dt square multiplied by dx plus capital D into dx by dt again multiplied by dx by dt. So that would be dx by dt whole square into dt plus k into x minus x0 into dx minus integration of fe into dx. Now again, if we look at the terms closely, the first term indicates the energy stored in the mass. The second term, that is d into integration of dx by dt whole square into dt, indicates the heat loss due to the friction, and the third term is nothing but the energy stored in the spring, that is Wms. So the total energy transferred to the coupling field from the mechanical system would be minus of integration of Fe into dx. Okay, so Fe is the positive force with positive displacement dx. So since we are moving in the opposite side, we are taking this as minus, but Fe is nothing but the positive force in the positive displacement dx. Okay, so now as we have seen in the previous equation, my Wf was nothing but We plus Wm. Now I am just substituting these equations here. So my We, as we have seen here, is nothing but integration of Ef into I dt. So integration of Ef into I dt, and my Wm is nothing but minus of integration of Fe into dx. So this is what it looks like. Since this is negative, all the mechanical forces towards the coupling field would be in this particular direction. So this is the multiple mechanical and electrical input system providing their inputs to the coupling field. Now let us assume that in the electrical system we have J inputs. So the inputs would be like WE1, WE2 till WEJ. And in the mechanical system, let us assume that we have K inputs. So the input nomenclature for the mechanical side would be WM1, WM2 till WMK. So the energy supplied to the coupling field may be expressed as WF, which is equal to the sum of WEJ, where J is from 1 to capital J, and plus that is the addition of electrical inputs plus the mechanical inputs. So the mechanical inputs is WMK, where K is from 1 to capital K, where capital J and capital K are nothing but electrical inputs and mechanical inputs respectively. So the total energy supplied to the coupling field at the electrical inputs would be WEJ. So sum of WEJ, which is equal to integration of EFJ into IJ into dt. Now how did we get to this particular equation number 12? So for this we have used the equation, this equation number 7. WE is equal to WEF into I dt. Now when we have more than one inputs, we have modified our equation substantially. Similarly, if we want to find out what is sigma WMK, so that is equal to minus of sigma FEK into dxk. Now again, how did we get this equation number 13? So we got this equation number 13 by modifying my equation number 9. Equation number 9 is just for a single input. If we have multiple inputs, we will modify our equation accordingly. So now using this equation, we come to the energy balance equation. So energy balance equation is nothing but my WF, which is the addition of both my equation number 12 and equation number 13. So if I both add them up, I just substitute the right hand side of the equation number 12 and equation number 13 in my equation number 14. So this is what I get. And if I want to remove this integration sign, so in the differential form, I can write this as d of WF is equal to sigma EFJ IJ dt, where J is from 1 to capital J, that is the total number of electrical inputs, minus sigma K is equal to 1 to capital K of FEK dxk, where capital K is the total number of mechanical inputs. So friends, that's it for today's lecture. If you have any doubts, feel free to write to me on my email address as mentioned in the description, or feel free to comment in the comment section. Thank you and have a great day.